So we've talked a little bit about patterns in inductive reasoning. We talked about that a conjecture is an educated guess or an unproven statement. I'm actually going to add that to this definition, an educated guess or unproven statement based on an observation. And that inductive reasoning is basically a process of making conjectures and recognizing patterns. And I want to talk us through a couple of examples now. For example, if I were to ask what grade are you in, if someone were to ask me that, now I can't see you, obviously, so I'm talking to a lot of you, so I can't say exactly what grade that you are in because I'm talking to people from multiple grades, but I can make an educated guess that you are in 9th or 10th grade. And why do I know that? Well, because I know that students at Providence that are in geometry are typically in 9th or 10th grade, right? So I can make a conjecture that everyone that's watching this video is in 9th or 10th grade. Now, to actually prove that statement, I would need to go through and make sure that everyone that is watching this video is in 9th or 10th grade, but this would be my conjecture. For example, I also could talk about where did you go to school last year? Well, there are typically a few examples of where people go to school. You may have gone to Providence last year, but you may not have. But even if you may not have, I can make an educated guess on where you went to school. For example, maybe you went to Perimeter, or maybe you went to Hebron, or maybe you went to Johns Creek, or maybe you went to Bridgeway, or maybe you went to Ardios. Because I know where Providence students typically come from, I can make an educated guess about whoever's watching this video, probably where you went to school last year. But here's the thing, if I were to say, my conjecture is that every student watching this video went to Providence last year. Does that necessarily mean that I'm always right? No, so conjectures can be wrong, but if a conjecture is wrong, you always have to provide a counterexample. Okay, and a counterexample is defined as this. A counterexample is an example that proves a conjecture to be false. An example that proves a conjecture to be false. So for example, let's go back to my last example where I said that all students watching this video went to Providence last year. If I know that a student instead went to Perimeter last year, the counterexample would be to say that can't be true because here is this student X, fill in the blank, that went to Perimeter last year. That is a counterexample. And we always need to provide counterexamples when we are making a conjecture. Let's practice making a couple of conjectures right here. For example, here is a conjecture. X squared is always greater than X. How do we begin to unpack whether or not this is true? Well, we start by just trying some examples. For example, the simplest example is always pretty much going to be either 0 or 1. So let's try that. Let's try 0. If X is 0, then this is 0 squared. And this is 0. Oh, well, 0 squared. 0 times 0 is just 0. And 0 being greater than 0 is not true. So this conjecture would be false. So something that you would originally think might be true just by looking at it saying, yeah, that's probably true, is not true in every case. And this is the counterexample. Okay, so this is what we would use to say that this conjecture is not true. We would say, well, if X is 0, then this is not true. So the conjecture that X squared is always greater than X cannot be true. Okay, let's look at this example and let's talk about making a conjecture. What is the sum of the first n odd positive integers? Now you probably just read that and went, what the heck does that even mean? Let's talk about that for just a second. And that's a totally normal reaction. This is a lot of words that takes time for us to process. So what is the sum of the first n odd positive integers? Well, what does n mean? N is just a typical variable that we will use that means any number. right? So any number. So what is the sum of the first n odd? So we're only looking at odd. We're only looking at positive integers, right? So whole numbers. And so think about this. What if n is 1? Here's how we can read this. What is the sum of the first 1 odd positive integers? Well, the first odd positive integer is, of course, 1. And if we're not adding anything to 1, then the sum is just 1. Okay, so let's go up to the next example. What if n is 2? Okay, then this would read, what is the sum of the first 2 odd positive integers? Well, the first 2 odd positive integers are 1 and 3. And what are we doing? We are finding the sum. So this would be 1 plus 3, and the answer to 1 plus 3 would be 4. Let's keep going. What if n is 3? Then we would need to be adding together the first 3 odd positive integers. So that's 1 plus 3. And then what's the next odd positive integer? That would be 5. 1 plus 3 plus 5 is 9. Let's do one more. What about when n equals 4? Well, when the sum of the first 4 odd positive integers would be 1 plus 3 plus 5 plus 7. And that is 16. Okay, why am I having you do this? Well, here's why. There are lots of questions like this in math where we can come up with really cool rules. For example, let's look at all of these answers. The sum of the first odd positive integer is 1. The sum of the first 2 odd positive integers is 4. The sum of the first 3 odd positive integers is 9. The sum of the first 4 odd positive integers is 16. Can you notice anything special about these numbers? Have we seen these numbers already in this section? Or another way to ask this question is, do you see any relationship between what n is and what our answer is? And hopefully that you should be seeing that, yes, whatever the sum ends up being, then the answer, that is always going to be the square of whatever we choose for n. So for example, if we choose n as 1, then the sum is just 1 squared. If we choose n as 2, then the sum of the first 2 odd positive integers is 2 squared, which is 4. If n is 3, then this is 3 squared. And that is a pattern that holds true for all of the odd. If you wanted to know the sum of the first 1,000 odd positive integers, you wouldn't have to actually sit there and go 1 plus 3 plus 5 all the way until you've counted to 1,000 odd positive integers. You would just need to do 1,000 squared, right? So the sum of the first n odd positive integers is always just going to be n squared. That's a pattern, and we have now made a rule about that we don't have to do all of this kind of laborious arithmetic to get this answer. We've noticed a pattern and have been able to make a rule about that pattern, that the sum of the first n odd positive integers is always going to be n squared. So when I ask you a big question like, hey, what's the sum of the first 30 odd integers? You don't have to go, okay, and count, okay, 1 plus 3 plus 5, so on and so forth, right? All you have to do is go, okay, because I noticed this pattern earlier, I can do this really quickly. I know that the sum of the first 30 odd integers is just going to be 30 squared, and 30 squared is 900. So if you sat there and you added the first, and you did this, and you wrote down 30 of these odd positive integers, guess what you would get? You would get 900. And if you don't believe me, you should take the time to do it. But this is why patterns can be powerful. This is why patterns and using inductive reasoning can be a powerful thing in math, because what we're able to do is when we recognize these patterns, we can try and describe them, like saying this pattern, okay, each of these sums end up being squares of those numbers, and then what we do is we make a rule about it. We generalize it, and we say, okay, so in general, the sum of the first n odd positive integers is always going to be n squared. So that is your first lesson in geometry, that most of geometry is just sitting back and trying to process. It has very little to do with finding a right answer. It has much more to do with looking out and recognizing patterns.